Okay, so in this week's lab, we're going to be looking at animal circulation, and we're going to be using the organism Daphnia to look at animal circulation. So as you can see, here's a picture of a Daphnia, and they have a clear exoskeleton, which enables us to be able to see the internal organs of the Daphnia. And so this top one's a female, as you can see. Here are the eggs, and then this bottom part is this bottom image is a male, which is labeled. And so as we can see right here on the dorsal part of the Daphnia is the heart. So just a quick review, Daphnia do use an open circulatory system in which they pump hemolymph around their body. And so they use hemolymph as their circulating fluid for gas exchange and is not confined to blood vessels. So as you can see in this diagram right here, we have the heart, and it pumps that hemolymph around the body as the gas is exchanged through the body also. And so as I showed in that diagram above, or that picture of the Daphnia, the heart is right here. And so I'm going to show you a YouTube video, and you'll be able to see how it resembles the movement of thoracic appendages. And this is what you'll be looking at in lab, so this will give you a little bit of familiarity with what you're looking for exactly. So as you can see, here's the heart, and it's pumping that hemolymph around the body of the Daphnia, and you can kind of see the movement of the hemolymph down in here. Okay, so that'll kind of give you an idea of what you're looking for in the lab. So then quick overview of the life cycle of Daphnia. So they have a sexual cycle and a parthenogenic cycle. And so the sexual cycle does produce females, and then the females can go either back into a sexual mating cycle, or they can go through a parthenogenic cycle in which they can create a parthenogenic daughter or a parthenogenic son. And then these two can go again either through the parthenogenic or the sexual cycle, and where the female will mate with the parthenogenic son. So what we will do in lab is there's going to be 3 parts. So the first part is observation, where you will take 4 15-second measurements of the Daphnia heartbeat. You'll calculate the average, the standard deviation, and the standard error, and then you'll share those results with the class. And this will kind of give a baseline of what you're looking at in terms of the cardiac output of Daphnia. And so the second part is going to be where you're going to design 2 experiments using 2 treatments. And so then each experiment will have 5 Daphnia control and 5 Daphnia for treatment with multiple trials per individual. And so you will choose 2 treatments from this list to subject the Daphnia to and then monitor their heart rate. So we have ice, we have a hot plate, caffeine, alcohol, or ethanol, acetylcholine, adrenaline, salt solution, sugar solution, and carbonated water. So I'm just going to go over real quick what some of these chemicals are, such as acetylcholine. So in humans and other animals, heart rate is slowed by the parasympathetic nervous system using a neurotransmitter acetylcholine via activation of the cell surface receptors in the sinoatrial node called the acetylcholine, which are basically the acetylcholine receptors. This occurs after feeding, during sleep, and during breath holding and swimming underwater. And so the slowed heart rate is associated in the rate of ejection of blood from the heart to be sufficient to maintain body function during rest, and then conserves energy in the heart under conditions where its supply of oxygen is diminished. And so this drug does slow heart rate. And then we will also be using adrenaline. And so the heart rate is increased in this case by the sympathetic nervous system with the neurotransmitter noradrenaline, and then the hormone adrenaline circulating in the blood via activation of cell surface receptors in the sinoatrial node. And so this occurs during exercise and fear. And so basically the effect increases the rate of ejection of blood by the heart. And so that means there will be more blood flow to the skeletal muscle, and so skeletal muscle cells are supplied with more oxygen, and respiratory substrates used to generate more energy where it is needed. So then we can also get caffeine, which also has the same exact effects as adrenaline and noradrenaline, and so it also increases the heart rate of the individual. And in humans, it can increase 2 or 3 cups of strong coffee or tea that contain enough caffeine can cause an increase in humans of about 5 to 20 beats per minute, which doesn't sound like a lot, but can be substantial. And then we'll also be looking at ethanol, which is alcohol. And so as we know, ethanol does slow the heart rate. And it does cause effect in humans and cause effects with other organisms also. So what we'll be do this week is you will look at, you'll type up a results, discussion, and references. And then, so look at the lab report for instructions to guide you on this. And then you'll be creating tables and figures in this. And we'll go over like what we expect of the tables and figures here in just a second. And then you'll also have your regular question packet that will be due. Both are due next week. I'll say that again. Both are due next week. So let's take a look at standard deviation. So basically, standard deviation is the spread of numbers and how close they are to the average. So we'll watch this YouTube video here on what standard deviation is.
File with the help of an expert, or let an expert file for you. Intuit TurboTax Live.
We got lucky. We got
Gucci
two
guilty.
ads.
Eau de toilette pour homme.
And parfum.
Okay.
Have we discovered a new particle in physics? Is a manufacturing process out of control? What percentage of men are taller than LeBron James? How about taller than Yao Ming? All of these questions can be answered using the concept of standard deviation. For any set of data, the mean and standard deviation can be calculated. For example, 5 people may have the following amounts of money in their wallets: $21, $50, $62, $85, and $90. The mean is $61.60, and the standard deviation is $28.01. How much does the data vary from the average? Standard deviation is a measure of spread, that is, how spread out a set of data is. A low standard deviation tells us that the data is closely clustered around the mean, or average, while a high standard deviation indicates that the data is dispersed over a wider range of values. Standard deviation is used when the distribution of data is approximately normal, resembling a bell curve. Standard deviation is commonly used to understand whether a specific data point is standard and expected, or unusual and unexpected. Standard deviation is represented by the lowercase Greek letter sigma. A data point's distance from the mean can be measured by the number of standard deviations that it is above or below the mean. A data point that is beyond a certain number of standard deviations from the mean represents an outcome that is significantly above or below the average. This can be used to determine whether a result is statistically significant or part of expected variation, such as whether a bottle with an extra ounce of soda is to be expected or warrants further investigation into the production line. The 68, 95, 99.7 rule tells us that about 68% of the data fall within one standard deviation of the mean. About 95% of data fall within 2 standard deviations of the mean, and about 99.7% of data fall within 3 standard deviations of the mean. The average height of an American adult male is 5'10", with a standard deviation of 3 inches. Using the 68, 95, 99.7 rule, this means that 68% of American men are 5'10", plus or minus 3 inches. 95% of American men are 5'10", plus or minus 6 inches, and 99.7% of American men are 5'10", plus or minus 9 inches. So, this means only about 0.3% of American men deviate more than 9 inches from the average, with 0.15% taller than 6'7", and 0.15% shorter than 5'1". This reasoning suggests that LeBron James is 1 in 2,500 and Yao Ming is 1 in 450 million. In particle physics, scientists have what are called 5 sigma results that are 5 standard deviations above or below the mean. A result that varies this much can signify a discovery, as it has only a 1 in 3.5 million chance that it is due to random fluctuation. In summary, standard deviation is a measure of spread. Along with the mean, the standard deviation allows us to determine whether a value is statistically significant or part of expected variation. Thanks for watching. See you next time.
Okay, so that's just a quick video on standard deviation, and we are going to watch another video here that's going to be important in creating your data.
In this second video, we're going to learn how to calculate our mean and standard deviation, and then use those these statistical measurements and this information to actually graph our data and to take a look at our data and kind of analyze it a little bit more. So what I have here set up is this is data table 2 from our potato membrane diffusion lab, and I've got for our different trials and for each of our different molarities, I have the percent change. So this would have been one group, group 1, trial 1, and this is their percent change for all of the different molarity concentrations, from distilled water at 0 to full 1 molar change. And then it goes through the 9 different groups. And I want to calculate the mean and the standard deviation of these different values. And so to do that, Excel will actually do this for us very easily and very quickly. And again, we're going to be using an equation. So I'm going to type equals, and the mean is just the average. And Excel already has this equation built into it because it's one that's used pretty frequently. And so if you start typing average, AV, you see that it already pops up right here. It says average. So I'm going to click on that. And now it's asking for some numbers in between these two parentheses. So it wants us to highlight a set of numbers that we want it to calculate the average or the mean for. So I'm going to highlight this first column here that is 0.0 molar. So I've highlighted B, column B, number 3 through 11, and it shows that right here. And next I'm going to press enter. And this is the average for 0.0 molar. So for all of our trials, our average is 12%. Now, as we learned in the last video, I don't have to do that for all of these. I can actually just have Excel copy that formula for all of them. So if I move my cursor to the bottom right hand corner of this cell, my cursor changes to a black cross sign. So I'm going to click once with my mouse and drag that across all the way to 1.0 molar, and that's going to then calculate the average or the mean for all of these different values. Let's check one of these. Let's check 0.6 molar just to make sure. If I click on this, if I look up here in my formula bar, if I click on it, it'll show us what's being highlighted, what's being calculated. It says the average of E3 to E11. E3 to E11, that's what I want it to do. So that average is a negative 23%. That means that that potato is actually losing mass. So again, this is the percent change in mass, so a negative number is going to represent that that potato is losing mass. Next, we need to do standard deviation, and this is just as basically as easily as calculating the mean. We're going to insert an equation again, so I'm going to press equals, and I'm going to write standard, and you'll notice it already starts pulling up some different options. When we're calculating standard deviation, we want to use the STDEV equation. So I'm going to click that, and I'm going to highlight our group of samples, or our numbers here. I'm going to highlight this row B3 to B11 and press enter, and there it calculates our standard deviation for us. I only have to do that once for this one cell. I can now click on this box like I did for the mean, drag it over, and all of our mean and standard deviation is calculated for us just like that. So now that we have our mean and our standard deviation, our next step is to actually take this information and graph it. And in order to do that, I need to change how our data table is set up a little bit, or I need to make a new data table. So I'm going to do that right here. And the first thing I'm going to do is in a column, I'm going to put our molarity of sucrose, sugar. So we have 0, 0.2, 0.4, 0.6, and 0.8, and 1.0. We need to add an M to this. Let's make this column a little bit bigger here. And the next one, I want to add the mean percent change in mass of solutions. By setting up this little data table right here and actually taking the time to label our information really well, it's going to make making our graph easier. and I need to actually add units to this, so I'll do that. This was in, no, I guess I don't need to do that since it's just percent. And so to get our mean values here, I can actually have Excel do this pretty easily for me. So I'm going to type equals and just click on the box that I want, which would be 12% for zero molarity. Press enter and do the same for the rest of these. Unfortunately, because it's not in a vertical column, the mean right here is not in a vertical column, you can't do the drag feature. It won't work for this. So I've got these values here set up. I've got my molarity and my mean percent change in mass of solutions. I think we actually should add units here. We've got plus or minus 0.1 grams. So now I want to turn this into a graph. And to do that, I'm going to scroll down a little bit here. To do that, I'm going to highlight all of this information, these two A and B columns, and then the rows 17 through 23. I'm going to highlight those, and then if I look up above on my toolbar, right up here, there's a tab that says Charts. I'm going to click on Charts, and I want to use something called a scatter plot. So I'm going to hit this little down arrow, and I want a marked scatter plot. This is what we're going to use. And if I click that, it'll insert the chart for us nicely. And you can see it's already got our title here, which is really nice. It's got our horizontal values right here, 0, 0.2, 0.4. These are different molarities. I'm going to make this a little bit bigger so we can see it. There we go. Make that a little bit bigger. And I'm actually going to delete this series name. We only have one series. We only have one group of...
Okay, anyways, this is just a video showing you guys how you can look at Excel and whatnot. But if you do need more help, we can, with this, I do encourage you to look up this video and look at how to use Excel. Don't worry about any of the terminology in terms of like molarity and stuff in that video. It's just supposed to show you about how to use Excel to find average, standard deviation, make scatter plots, etc., etc. So let's go talk about like what we expect of your plots and your figures in your tables to look like. So it's a good figure, right? Well, no, not at all, because we don't know what's going on with this figure. There's a lot that's missing to it. So what we want is we need a title, we need a key, we need units, we need labeling of the X and Y axes to be able to understand what exactly we're looking at with the figure specifically. So make sure that you're including these. Trend lines are good. Also, you want to make the figure as clear as it can be. Someone should be able to look at the figure and then understand what they're looking at. And then if they need more beyond that, then go to the figure legend. So just kind of looking at the figure. So again, here we have it in a y-axis label, origin, x-axis label, x-axis. We have the data. We use symbols for the data. We have a key if there's multiple symbols used for the data. And then, which you will be using multiple symbols for the data if you're comparing across the heart rate, so a key is necessary. And then the figure goes below the figure. And so generally, that first sentence of the figure is the title of the figure. And it's very plain and simple. And so as you can see, the first sentence is cumulative germination of seeds after pre-germination treatment of 2-day soak in sodium chloride solutions. And so it's just stating like what exactly we're looking at on the figure. And then for tables, it is a little bit different. With tables, the table legend goes above the table. And so then you have your table, you have your column titles, your table body, which is the data, and then you have footnotes. If you use any kind of symbols like up here on the populations, then make sure you have a footnote that shows what those symbols mean. So anyways, that is that. If you have any questions or anything, feel free to email us. This is what we'll be doing in lab this week. Look forward to seeing you there. Bye.